hello to everybody. And we have the 2 talks already on absolute dating. We had one talk by Urschaltegger on the uranium-lead dating, and then we had a talk of Sébastien Nomade on argon-argon dating. And now I'm very pleased to have now Stein and Judith from Colorado University, and they will speak about rhenium-osmium dating of organic rich shale. And I'm very pleased that you could make this talk, and from Colorado, so you are 8 hours earlier than us, so it's quite early for you, but thanks for the effort, and it's all yours now, and you can start with us.
Well, thank you very much for this opportunity, Jacques. I'm Holly Stein, and it's Judy Hanna, and we're going to kind of co-present this as a team. And outside my door here, we're in Colorado, and 7 in the morning, but outside the door is the rest of the team hard at work in the lab. They come in early and they're already on it. And so we're going to talk about some of the accomplishments of the group and some of our early work initially in how we figured out to tease time out of the sedimentary section, shales in particular. Boers talked about uranium lead dating, and you have to have a tough bed, or you have to have something with zircon in it. The only zircons that are in shales are detrital zircons, so they can be much older, a big assortment, wide ranges. But the shale itself, the depositional age of the shale, is captured in the organic material that we extract from that shale. So I'm going to walk through a couple of examples that we did, and I think importantly for the audience is to tell people how we take apart that shale and how we handle the data that we derive from that shale, because I'm very happy with the way we work with the data, and we've spent a lot of time thinking about that. So with that, let me just get started here. You'll see these nice fossil ammonite. It's the subcuttini species, or my paleontology isn't good, but wait, one point I want to make is that we love working with stratigraphers, paleontologists, you know, and that's what makes geology is it's a messy, heterogeneous thing that we have to work with. And that's what kind of tightens the story and pulls it all together. So just one background slide here in the box in the middle, that's what we're going to focus on today. But rhenium osmium really started out with the meteorite community, because meteorites have lots of rhenium and osmium. And this is where some of you in Jacques' group will have more familiarity perhaps. And from there in 1997, we developed an application in crustal rocks to the mineral molybdenite, MOS2, molybdenum disulfide. And I call this the zircon for rhenium osmium dating. And from there, we broadened our application to arsenopyrite and pyrite, which is a very common sulfide, and started to apply the chronometer to other sulfides, and then used osmium as a tracer. You'll see that in a minute, how that works, for where the fluids are that form these ore deposits, these sulfide-rich environments. And from there, at the same time, our colleague Rob Creaser up at Alberta was working with Shales, and he and his postdoc Dave Selby, they came down to visit us in 1999 to figure out how to do molybdenite. We shared with them, and in about 2000, Rob invited us to Alberta, and we were not faced with reinventing the wheel to date shales, but we got a leg up to get going on that. So sharing between groups, which is the way life should work, good science should work. And from there on, we won't talk too much about this, but these working with hydrocarbons and oils, things that are generated after a shale's deposit, maybe 100 million years later, these are the things that you have to be careful with in shales, because they can disturb the rhenium osmium clock. And there's just a huge amount of work that we've done on dating, direct dating of oils and so on. And I'm only going to have one slide just to say this is where we can compromise the clock at the end, because this talk today is going to focus on how we take apart shales to tell time, geologic time. Okay, but you should know that this is it's been a process, and rhenium osmium is now, certainly for sulfides, very, very solid technique for dating. Whoopsie, got to go the right way. Okay, rhenium and osmium, for those of you not studying the periodic chart every day, these are the platinum group elements. Ruthenium, rhodium, palladium, osmium is one of them, rhodium, platinum. And then they're called PGEs. Maybe you've seen that. And rhenium is not a PGE, but they share, rhenium and osmium share similar geochemical character. So rhenium, osmium, and shales, today's talk and topic. Shales are enriched in organic matter. And I don't know how much those of you with a basic geologic background know that there's a couple components to shale, and one is a clastic component. And that is a very, very fine-grained silicate material. We think clastic sandstone or something, but in a way, it's just an extremely fine version of that. It's a size designation. And the rest of shale can be enriched in organic matter, especially a black shale. So how much enriched? A few tenths of a percent of what we call TOC, T-O-C, total organic content, or it can be 30, 40, 50% in a very, what we call asphaltene rich shale. Now, this organic matter contains redox sensitive elements like molybdenum, rhenium and osmium, uranium, several others. And those elements are trapped in, attached with the organic matter, and they reflect what the seawater conditions were at the time. So if you have super high rhenium in a shale, or molybdenum, or any of these elements, then somehow that seawater, in the most general sense, has delivered that into the organic material, which then becomes sequestered at the bottom and later is lithified into shale. And so the amounts of these redox sensitive elements, among several things, but they primarily reflect the degree of continental weathering, if you have submarine volcanism and venting, hydrothermal venting. And as I said, they're fixed in these anoxic or eusinic, meaning sulfide bearing, in addition to anoxic without oxygen bottom sediments. Now, rhenium osmium then has a perfect application here. Rhenium, the isotope 187, decays to osmium 187, and you can calculate from that, knowing the decay constant, the time, the age of the organic material, which is the age of the shale, provided there has never been any opening of that clock by oxidation. That is death for rhenium osmium. Any kind of subsequent oxidative fluids moving through the rock will disturb the chronometer. And then I will go through this, but one of the things that falls out with the dating is this tracer. It's just like rubidium strontium isotope tracer. We're more familiar, that's been in textbooks longer, but it's a tracer that tells you something about the seawater at that time. Very briefly, if you have the mantle value for 187, 188 is about 0.12 to 0.15 today, very low. Crustal rocks that have a lot of rhenium in it that are old, for example, those numbers that we measure can be in the range of 1 to 10. So you see a very big difference between a mantle signature and a crustal signature for an osmium ratio. Okay. And I kind of talked a little bit about this, but very briefly, there's 2 isotopes of rhenium and 7 isotopes of osmium. And what I mentioned is that this is the clock by abated decay. 187 rhenium decays to 187 osmium, which in the whole bulk Earth, or like a meteorite, is a very small amount of the total osmium. So it's very easy to, if you have high rhenium in shale, it's very easy to increase this significantly, the mole fraction of the 187 osmium in the total osmium content. Now, where they share characteristics, they're both chalcophile, siderophile elements. Chalcophile, they love sulfur. Radium and osmium like to be associated with sulfur and iron. And the chronometer is has an enormous range for those of us working on planet Earth. It's 10 times the age of the Earth. So we can date things that are very old back in the Archean. We've dated some molybdenites in the Archean, and also very young. For example, fumaroles today that are forming the mineral molybdenite, or even there's a mineral called rheneite, rhenium disulfide. And if you have a parent amount is a sulfide that is tens of % of the mineral, then in a very short amount of time, you can make a lot of daughter osmium. So we can date things that are very young in certain environments with molybdenite and rheneite sulfides. Now, one of the unique things about rhenium osmium, particularly when compared to uranium lead, is that the reservoirs for these two minerals are very, very confined. The simple statement is they do not take residency in silicate minerals. This is very convenient for the clock because, you know, when you have uranium lead, you can have uranium lead in a host of different minerals that you have to keep track of as you try to tease time from a section. Here, rhenium and osmium are associated only with organic rich component of shales, not the clastic, the small feldspar and mica and quartz that makes up significant component of a shale, but only the organic material. They're associated with sulfides, as I mentioned, and they can move about if you form hydrocarbons from the shale. So you have heating, pressure, and the kerogen, which is the organic component in shale, may break down and you form bitumen or oil. And there is an easy mobility there with the rhenium osmium moving from organic material and kerogen or partially moving into the hydrocarbon, bitumen or oil. So it's, in a way, it's very easy to keep track of these reservoirs. I think Judy's looking at me like I should hurry. Okay. So this is our little clock. Radiometric clock to date sulfide bearing systems and organic rich rocks. And this is really a unique thing with a chronometer because it covers a part of telling geologic time that can't be covered by other systems, uranium, lead, argon, and so on. Okay, now it's very simple. Rhenium and osmium, it all comes down, when you make an isochron there in the center, it all comes down to the equation of a straight line. We determine this ratio, which is y equals b plus xm. We measure and determine this. We measure and determine this, and we have an xy plot or coordinate that we can put on an isochron. And this is the decay constant, the rate of decay of rhenium-187, and we solve for t time through the slope of this line. Now, absolutely critical to the chronometer working is, as I said, no subsequent attack on the clock through oxidation or the system becomes open, and then you start moving parent and daughter differentially in and out of minerals, and then you can't date. You can't date the material. And a fundamental assumption is that all of the samples had the same initial ratio. Well, seawater is, you could think of it as a giant bathtub practically of, there are variations, I'm generalizing here if you have a restricted basins, but you have to have all the same initial ratio in the samples. And the only thing that varies is the rhenium to osmium ratio in those samples. And so if they're all the same, the higher the rhenium, the more radiogenic daughter osmium over here you're going to produce with time. So higher rhenium osmium ratio, samples to the right here, will grow faster. And we measure, what we measure today is we analyze the samples and they line up if everything is perfect on a line. And you'll see that in the right sampling does that pretty well. So when I show these examples, so that people who are on this later on the Zoom or the YouTube, looking at the YouTube talk, they can go and look up details on their own. But one of the things early on, part one, it says sampling protocol. We firmly established this and others have followed, but you have to use drill core. If you use outcrop samples, you may have some incipient weathering that can cause scatter in the isochron, weathering, oxidation. So I'm going to move a little bit faster here. And we work, because our whole program is on soft money, which is an enormous challenge. We were talking about that beforehand. Nobody has salaries and the lab is not supported at CSU. But what we've done is establish really good relationships with industry and made ourselves sort of invaluable to some of the work that they're doing, and received support from that. I have a thank you slide at the end of our largest sponsors. But we go to the core facilities with people from industry and we collect the core together. We decide with them, we show them what we're looking for, what I've just described to you. And what does it look like if we have a piece of core? Well, then we had to take a CAT scan of it. And what looks like a black rock here in the section, this is a reservoir rock with oil, but here are some black pieces of core. Here, Judy's looking at some, but they have some bronze areas where there's pyritized fossils, which are good for dating. But if we put that in a CT CAT scan and look at it, there's a lot going on in a piece of mundane looking black shale. Here we see framboidal pyrite snow. And a lot of those framboid pyrites are in the water column and they are drifting down and then become part of the sediment record. Or we see burrows. We used to think burrowing, oh, this is bad. But those burrows that are pyritized, that's why you see a density contrast there. Most burrowed samples actually can be dated very easily because those burrows that are pyritized form very close in time to the sedimentation within our ability to do our analytical error. So the take-home message is thoughtful strategic sampling. If you don't use drill core, there's no way to interpret scatter on an isochron because you don't know if it's from weathering or what, or if you have a real age, but just a little scatter. If you do use drill core, the lack of isochronicity is capturing real geologic variation that then becomes fun to interpret and explain why. So this is just a quick example of how we take just a minimum amount, drill a minimum amount. This is a piece of black. Doesn't it look mundane after seeing those beautiful CAT scans, what's really inside? But we drill out and then we separate the organic component. That's a whole other talk using organic solvent. And then each one of these holes will be a point on the isochron. And it's absolutely critical that you work with small samples, that you don't crush all of this as a point on the isochron, or, oh, heaven forbid, you crush the whole 5 centimeters and say that'll be a point on the isochron. Because what you do is you homogenize out any real geologic variation in the osmium initial ratio that may be present. I'll come back to this a little bit later, but yeah, I'll just come back to that. But common sense sampling. Now, here's another version of what I just showed you. We often put a placer of some tin foil in when we take a sample out. So here's again another, what is it, 5-10 centimeter of core, and each one of these is point on an isochron. Again, I cannot emphasize enough, to evaluate the integrity of the chronometer in organic rich shale, you need to report all analytical results. And if there's deviation, that information is valuable and carries a geologic message. So always report all data, never pick data that are, oh, these are all on the line. But now I'm going to show you an exception of how we can pick through data. Here's what we measure. And this is the example, but I want to show you how we can look at where the aberrant, let's say, non-isochronous samples fall. This is a drill core. I think it's about 20 some centimeters, and each of our samples are a few millimeters thick, sort of abbreviated over here with these green lines. And what we measure is the rhenium concentration, uncertainty of the osmium, and then we measure isotopic ratios of osmium and rhenium and then put it together in this way. And from that, we derive isochrons. I'll leave this for you to ponder the details, but the point I want to make too is we only use a few hundred milligrams of sample. It doesn't take very much. So from that data table that I just showed you, these are the data, all of them shown. And you see a little bit of scatter, but the age is pretty much what we expected. But gosh, we'd like to have better than plus minus 3.7 million years. And the MSDWD, mean square weighted deviates, which is the amount that these points, the actual measurement is just this little dot. But I put a box around these so you can see them better. You know, it's hard to see dots down here when it's very small. And I see that the picture shifted just a little bit. The dot should be centered in the box there around it. But you see a little bit of scatter in these. And so what you do is you go back to your core and you evaluate where is that scatter. And you can make thin sections, CAT scans, lots of things to aid in this evaluation. But this is just a first level evaluation. This point is clearly a little bit above the line. What point is that? You go back to the data table, it's that point here. So if we take that off, and these are, you can't just take off points because you don't like where they are. You have to be very thoughtful about this. If we also then notice that these points kind of straddle the isochron, what two samples are those? Now remember, it's these two. So remember, this represents a stick of core. So now we have three samples together in one part of the core. They're a little bit off. Right here, we have 3 points that two of them are replicates. So it's really two samples because this is a replicate, but it's these 3 points and they're all a little bit shaky, a little scattered on the isochron. If we remove those 3, they are now at the bottom end of the core and we're left with, and notice how the MSWD came down from the last one, the error came down from the last one, a little better precision because the points are better fitted to line. But if we remove these last ones here, if we choose to do that, even if you do, you show all the data in the data table and you explain what you did. And you show these 3 ages and say, because those are the most scattered and they seem to be at the bottom and top of the core, which means there might have been some variation in the initial osmium ratio. And then we can look at the center part of the core here and get a much better age with a improved uncertainty and much improved, what was it, 126 at the beginning, much improved mean square weighted deviates. But that's the kind of exercise that you perform going from the geology to the geochemistry and looking at those. Now, if you have scatter that is just random through here, then it's best not to throw any of it out and just say we have a lot of variation in that. But regardless of what you do, all data gets reported. So here, the 14, 13, 11 points, a little exercise. The number of points on an isochron was geologically driven. Not, I'm going to pick off these points. They're not, you know, they're kind of off. But it was geologically driven in the center part of that core, then gave a much more precise age and a much better fit, as shown by the MSWD. Okay, so now I'm going to show an example, and this goes way back. This is one of the very first examples, first really big hits, if you will, that we had. We were the first to apply rhenium osmium to unravel marine paleo environment associated with a major mass extinction. And we did that with funding from the Norwegian petroleum industry through a Petromax grant. And what we wanted to do is to look at the relationship of Norway and Greenland because they began to move apart around 250 to 60 million years ago. And so we sampled a section here, drill core, right here, and a section on the mid-Norwegian shelf, industry supported funding here, and that's this core over here. And the question was, does this unit, lower turbidite, upper turbidite units, what is the correlation across this basin? And the industry is very interested to know that for their exploration models and so on. So we're of value not only academically, trying to move the chronometer into the sedimentary record, but also to industry. And that's important to try to find as much value as you can from your work. So we were told that the age of this Ravnefjeld formation right here, presumably correlative over here to the shelf, the age of that is Waterpingian stage. So we were expecting ages of 260, you know, something in that time frame. And instead, when we did that, you can look at the details in this paper. Instead, when we did the dating, we got the age for all of these samples that was right at the Permo-Triassic extinction boundary. What? You know, I mean, what do we have here? So greatly improve the time scale, move this, and was as I said, the first radium osmium examination of what that lead in, we're just in front of the boundary and then on it. So there's much more work that's been done now. This is an older slide, but it's easier to see, much simpler. But these are the data that we have here, and you can see our uncertainties from isochron. They're larger than we'd like. Now we have much better blanks and much tighter results on things. But these are the uncertainties in the uranium lead ages too, which are not tiny. And now there's much more, there's been some later dating. This was 2011. So again, we were using the data. I'm not going to go into this at all in this talk, but there's a wonderful story here where we showed that the rhenium osmium isotope geochemistry not only provided dates, but together rhenium and osmium could be used to demonstrate all three characteristics of latest Permian seawater that each of these has individual publications, when acidic, and here's the evidence. But rhenium osmium could show extreme anoxia, very warm seawater, and acidic, plus give timelines. Okay, so that was our excursion, a little background on this, and what we received, the cores were here and here, presumably, and what we got was Permo-Triassic ages. Now, I want to show you a little bit how we work our way up section. Now, here we had 40 meters of section. Now we're working with, as I showed earlier, we'll try to get ages out of a 5 centimeter piece and another overlapping 5 centimeter piece. But here we were looking at larger sections, but taking small intervals of shale. So we're going to look first at the Greenland one, and then at these in a little more detail. These are some of the names for them, but okay, we're in Greenland. We had one core, one dated interval, 252. Now, for rhenium osmium early days, this was pretty exciting, pretty good, pretty tight. It ties in a lot of the time scale stuff is, throughout the record is ±2. So we were very happy with this. And a very nice fit of the line omitting this point, a very nice mean square weighted deviates. This should be ideally around 1. Shales, you rarely get to that. So just because of the nature of shales and the heterogeneity that you deal with in the sedimentary environment. But this was the age from Greenland. And presumably that this Greenland was postulated to be correlated to the mid-Norwegian shelf, the lower laminated unit. And we'll take a look now at the mid-Norwegian shelf. We had 4 sections that we did from there. The first was this bottom shale. And if you look at the geochemistry story, this is a normal looking shale. So things went really wrong in the latest Permian when we look at these 3. And it has kind of average normal rhenium osmium ratios as well. But this is high. We don't like that. And not a very precise date, but you take all the data. I think in the paper it says, I think we left this one off, but there's a lot of uncertainty and wobble in this line. Thus, we have the larger error there. Now, if we move up, still in the mid-Norwegian shelf section to the next core that we took, presumably correlates with the East Greenland based on spores and pollen. But, we can't go to the core box and say, here's the East Greenland core, here's the mid-Norwegian core. They're both black, so they must be the same age. You don't know what you're sampling unless you have a pollen person right there. And even then, the biostratigraphy, for example, pollen and spore material, it's spreading over a large amount of the stratigraphy. It's not just in one unit. So we took 2 black pieces from what was presumably correlative between the mid-Norwegian shelf and Greenland, East Greenland, and we got an age of 252. Nicer uncertainty on that age, nice MSWD, all points were on the line. So we love this, 28 centimeters shale. We didn't work with meters, we worked with 1 core this long to get that data. And that is absolutely imperative. Some of the early work was crushing a meter or 2 of shale, but you don't know how much time you have in a meter or 2. You could have millions and millions of years. You could have erosion, non-deposition surfaces, gaps that you cannot see with your eyes in the core, but they're there, gaps in time. So we take a small interval of time. Now, 252.5, how does that look with the Greenland? 252.1, these overlap beautifully. Now keep in mind, this work was done 15 or 16 years ago. This is some of the very, very earliest work in working with shales. So we were very happy with that result, good agreement. We could say, yeah, we're pretty close. Those units look like they're correlative across that seaway. The next one, I'll just go quickly through this, 252.2, the ages are all in the right order going up, even as the uncertainties includes the decay constant. The decay constant is about 75% of this number. So if you remove that magnifier, the decay constant, now you can start to compare ages with much, much lower uncertainties. But when you report on an isochron, you report the decay constant, so we can compare whether we're Schall-Tager's dates with the decay constant included, because these are two different techniques. And then last but not least, the fourth one, really nice, less than 1 million years. And again, most of that's the uncertainty, the decay constant. You take that out and we're talking really measuring at couple 100,000 years error. Nice fit, all points fit the line. And okay, so just to summarize, I went over this. This is the ash bed dating, and our dates are right in there with what the determinations were, the early ones for zircons and ash beds. Okay, I think I'll leave this for you to read the paper. I want to move on a bit. We talked about this. So basically, what does this mean? The ages are younger than we were told. They're at the PT boundary. They're not Witch-opinion stage. And initially, as we said, you could look in Svet Georg's paper, that the extinction may have spread, not be instantaneous, like the meteorite impact with the associated with dinosaurs. You know, this was instantaneous. And we'll visit something of that, but it may have spread around the globe, starting in the classic Meson section and reaching northern latitudes later. Or there was very, very fast deposition. The age of this formation is basically the age of this, because all of these turbidites are very quick. They can be very fast, loads of sand and mixed sediment squashing down and dewatering very quickly. So this was pretty exciting result. The other thing I barely mentioned, I just want to show you that the initial ratio here is not like the mantle. In other words, we cannot directly get the Siberian trap influence with a ratio like that in the seawater. And that's another thing that falls out from the isochrons. This intercept is the initial ratio at 252 million years ago. You see they're quite similar. And that suggests there was a good bit of continental input into the seawater. I mean, you have two continents breaking and spreading apart. But the influence of anything mafic, hydrothermal, mantle associated, or the influence of Siberian traps, which are thought to have been responsible, has to include some more continental component. I just summarized this. And for the rest of the story, it's a great story about the other aspects of radium osmium work that we could track increasing toxicity in latest Permian seawater. So I'm going to leave these for you to read, but I mentioned industry, and we've been fortunate to have a lot of support from the petroleum, and we wouldn't be here if we didn't have some of that. And they really believed in us and gave significant funding to go develop this, run with this. And one of the things that the industry wants to know, you see these 4 sections here, or 3 sections, sorry, and they're in different places in what's one of the oil-rich areas in the Barents Sea, the North Sea further south there. They don't know what piece of the source rock, the upper Jurassic is one of the richest source rocks through all geologic time. They want to know at various locations which part of it do they have, particularly as one of these members is very, very rich. So we went in and dated different krill member, algal member, and put this together for them, where they were at different locations in what we determined to be 19 million years of incredible anoxia. I don't know what else to call it. One of the most amazing source rocks for oil in the world. Okay. Judy's going to touch a little bit further on this with the Bayesian, but again, we went inside this upper Jurassic. It's called the Kimmeridge in one place. It's called the Jet in others. The Mondel Formation, the Häkkinen Formation. It's very confusing because it has many, many different names depending geographically where you are in the North Sea and Barents Sea. But we went in and dated, worked out ages for intervals of those. And you're going to cover that. Yep. Which I'll turn it over in just a little bit here. So another thing, this was a new discovery in the Barents Sea, and I want to show you, this is another way how you work with the rhenium-osmium clock in shales. We sampled 5 pieces of core, all 5 to 10 centimeters long, over 14 meters of this Upper Jurassic source rock at this locality where there's a new discovery. And if we take all the points from each of these cores, because we have an isochron for each one of these, put them here, this amazing plus or minus 300 million years for this 14 meters of core. This is rubbish. You can't do that. If you're thoughtful about it, 14 meters of core, you get millions of years of time. You can't say that's all in 300,000 years. And the reason it's rubbish is if you go to each of those pieces, like this could be this piece, and another one look they all look the same when you're looking visually. That's why the CT scan is so informative. And if you have sulfide or eosinic or an oxic condition, then we have another piece, similar length from this depth, and so on up section. So if you take all of those pieces and make individual isochrons for them, the ages are, it's not 300,000 years. We have 5-6 million years in this 14 meters of section. That's how you have to work with this. It's not like, what are the best points I can draw off? What's the most things I can put on to get the tightest age? That age is meaningless, what I showed you before. So you could again go to this paper, that's why we put it here, and you can look at some of this, and we have did some dating of glide faulting in there, which was kind of really fun. And how did we know? The age, this is the piece here, 2012, this piece. And the ages we got here, it's been corrected here to show you how things stack up in the right order, the right age. But the initial ages we got here, up section, you would think they would be younger than the ages down here, but we got something that was way older. And we finally realized that this little calcite vein, a few millimeters wide, was actually a glide plane, a fault surface. And here in detail in the thin section, it's where geologists, you do your homework here, you see the movement in the breakage on this vein, this calcite vein, and you even see bitumen. It's asymmetric, fibrous calcite here. You see the bitumen in it on one side. You can barely tell that here. This is a bitumen vein. But anyway, we realized that we had a reversal in age. What's going on? We have a reverse fault, glide fault, where in this muddy, slippery stuff, a section has been thrust over, and we captured that. And in the paper, you could read the details of how we straightened that out. Now, what else? As I said, we always pair the dating with some kind of trace metal chemistry. And it's really, really important to do that. And we're now working a lot with mercury. And what you also find, each one of these, this is the 2018 piece of core, gap. This is the 2016 piece of core, gap, break. This is the 2012 piece of core. Look at this. You have these huge jumps in some of the trace elements that tell you you've run over a fault, reinforcing our interpretation of what was happening, and that had to be a small thrust. And the displacement was probably, I think in the paper, again, read 2 or 3 meters worth. But you're in slippery mud, and this happens. You have slumps and faults. I mean, mud is, before it's lithified, it's pretty slick stuff. Okay, well, so our purpose in doing this is we were trying to look through the Upper Jurassic again and look at the changing conditions in seawater, because the organic component that we extract from each of these is representative of the conditions in seawater at the time. And what we find from 160 million years to 140 in this Upper Jurassic environment, that the initial ratio for each of those isochrons, and this involves another study to combine this study here as well as the Scala study here, these red ones. And we see very clearly increasing input from riverine continental runoff, changing the isotope composition of seawater over a period of 10, 20 million years, or 10 here. So that was the purpose of what was the tectonic situation at that time, what was contributing osmium to seawater. Okay, I mentioned something earlier, glossed over it, meteorites. And this really drives home the point that you cannot just take geologic section and say, well, we have a date here, we have a date here, so everything must be, we'll divide by 5 and put dates in across here. If you follow what I'm saying. A date is a date, and it's only representative of that. You cannot incrementally go between dates and divide the section up and say, well, this it represents every million years or so. And here is the wonderful example of it. This is a meteorite impact in the Barents Sea, the Muller. The age of it based on cyst assemblages, algal blooms is thought to be about 142, plus or minus 2.6. Published in a paper, but this is a book on this whole Muller impact. So we have samples over a depth of several meters here from several drill holes that are on the margin and within crater here. And we get a very, very similar age. This is very satisfying. So the biostratigraphy is pretty much confirmed within 2 sigma uncertainty. And we have an initial ratio. And that initial ratio, remember 0.6 from previous things, is pretty typical shale initial ratio. Nice MST, very nice fit to the line. But the point I want to make is you have here 80 meters of section, of sedimentary record section. We dated this little part after this turbulent slump, gravity flows. This happened in days, hours. The impact happens, you have a big crater, there's huge literature on this, things come up, the walls cave in, things settle down. And our question was, how quickly does seawater recover from a meteorite impact? Because the signature on a meteorite impact will be mantle meteoritic looking, and it would be about 0.12. If we just went in that meteorite and looked at its osmium isotopic composition. But seawater recovered very quickly. You're back to normal seawater conditions. And if you just go to a sedimentary section and say you have an age here and you have an age here and say, well, these ages must be in between, just divide it in equal increments, that's just garbage, because this is the extreme example of how you could put down 100 meters of section in a moment in geologic time. So this is the first precise rhenium osmium dating of a bolide impact. And this is going to be coming out shortly. A postdoc, he's now has a wonderful position back in India, and he's got his manuscript together, and we're moving this forward. So, okay, now biostratigraphy. I have a couple slides, and then Judy's going to talk a little bit about Bayesian. This was on the opening slide. This is an upper Jurassic ammonite, sub-Cucini. I'm really bad at sub-Cucini. And here you see beautiful pyritized ammonite just on a bedding plane in the shale. And you see even preserved some of its, I forgot the fossil word for this, but it has some ornaments here on the side, some little, not hairs or little spines or something, but it's even preserved. It's beautiful. So we can go right in on a fresh shale, and we can date directly fossils. We can date the sedimentary record. And for the biostratigraphers, we can date their fossils. We date sulfide, we date organic material in the shale to tell time. And here's another example. These are graptolites in the Ordovician. I don't know how many of you know very much about graptolites. Of course, I learned what they were, and they were very prominent, and especially in Ordovician. And here we are on bedding planes. These are so prolific. There, you open any bedding plane on the core. We had a meter core here. And these workers, Mollitz and Alberg, have all the species in their overlap of each of these graptolite species. They look the same to us, of course, but then we learned again working with the paleontologists that, oh no, the little ornaments are different. And it's just so fun to work with people outside your field as well. And I encourage that for all young scientists, everybody. And so in this section of core that we had here, we started to decide, well, not only can we date the organic material, here in the shale, but why don't we take an X-Acto blade and tease these little bodies off the core and put them into the beaker and go through the several weeks of chemistry and measure them, because they should be the same age. They fell out of that seawater. These bodies are at equilibrium with the seawater, as is the organic material from bacteria and phytoplankton here. So they should be allowed on the isochron, and they do. And what was nice is they had much lower rhenium osmium ratio than the organic component of the shale, thereby pinning the isochron pinning the line so there's not much wiggle in it. And we dated the stage boundary in the Ordovician. How well are we doing? And here, the Ordovician had a little bit higher initial osmium ratio, 0.8. Today, the seawater is what, about 1? A little more than 1, I think, yeah. And nice MSW, very nice fit. And this is will be coming out soon. But how well did we do? These are from what is thought to be the Floating-Depingian stage boundary in the time scale. Floating-Depingian 470.0 plus minus, every bit as competitive as that. So rhenium osmium is a way, if you're careful with what you date, how you do it, we can even put the fossils in, is a way of putting time pins in the geologic record. And there's many more people now doing this, but this was, of course, I'm showing some of our work that I can talk about with ease. Okay, and Judy is going to cover this in just a moment. I have 2 more slides. The take-home message, I'm going to let her walk through this in the Bayesian applications with this. But again, we were looking at ammonoid zones and comparing with uranium lead. She'll talk about that comparison, and it looks pretty good, but you'll go over that. And the uranium lead has inversions in the time scale here. But this study was the first, provided the first radiometric dates that firmly tied the ammonoid zones in the boreal, in the northern part hemispheres, to the Tethyan realm, equatorial located. So the biostratigraphers, they have different fauna, but they think that this fauna was living there and this here, and they think it's the same time, but here we can actually tie it together around the globe. My last slide before I turn over to Judy here is that in this paper, and she'll talk more about this in the realm of Bayesian, reduction of uncertainties through Bayesian statistics, the big take-home message here, not only looking at another climate crisis, was that we suspected with the rhenium osmium work that the Ladinian stage in the Triassic period was way too long. It just could not be 12 million years. And we were the first to really show that it had to be much less. There are only about 4 million years in this stage. And in 2008, there was an alternate time scale available for the Triassic. It was the alternate, not the one being used. And our rhenium osmium ages confirmed a much shorter Ladinian stage, meaning the alternate time scale was the correct one for the Triassic. So very valuable work that can be done with rhenium osmium in sediments. All right, I'm going to turn it over to Judy, who's been very patient here, and she's put together, I think, 4 or 5 slides, and then we've got one concluding slide to tell you about Bayesian refinement, which is of interest, I understand, to you AstroGeo folks. So.
Well, excuse me, the fundamental problem we have trying to date cyclicity is we're looking at cycles, the most important one of 405,000 years. That's less than 500,000 years. So we've been looking at isochrons with uncertainties of 1, 2, 3 million years. That's too high. We're not going to be able to address the questions we want unless we can reduce those uncertainties. There are a number of ways of reducing that uncertainty. So I'm going to point out here that this is a section of the MOCRUS core. It's one of the ones we'll be looking at in this project we're going to get funded in the very near future. Cyclicity can be teased out of these records. And this red line, for example, shows the 405,000-year long eccentricity cycle. And there's some longer period cycles as well that can be teased out of this. The challenge with this kind of astrochronology is that what we get is a floating time scale. We know roughly from the biostratigraphy and the stages that we're covering something like 8,000 years through this section. But it's in kilo years, I should say, 8 million years. But we don't know where this time scale fits in the real complete time scale. We don't know where to put it. And that's what the rhenium osmium ages will give us that absolute time pin. Physicists hate it when I say absolute time, but what we mean is we've got a fixed radiometric time pin that we can put into the time scale, and then we can fit this floating time scale into the section and see where it belongs. So this particular section was put together by Alex Hudson, who's working with Steve Hesselbo. Okay, this was something that Holly showed, where we were trying to use our early rhenium osmium dates to compare the boreal ammonite stratigraphy with the Tethyan ammonite stratigraphy. And in this case, uranium lead ages, there was great controversy about this particular section and how old it is, because the uranium lead ages actually had inversions in them. The uranium lead ages their uncertainties are determined by shooting laser at a particular zircon, maybe 50 or 100 times, getting a whole suite of points, and then statistically dividing by n, so that you can get at the uncertainty in this scatter of ages. And when you do that, you get unrealistically small uncertainties. Obviously, when the section goes down from 238 to 40 to 42, oops, back up to 240, there's inversions in this. They can't both be right. And the inversions are in some cases well outside the reported uncertainty. So that's a problem. We went into the boreal section, and these were outcrop samples, which are always going to have a higher uncertainty. There's always a bit of incipient weathering that can create problems, but we got pretty reasonable ages. So uncertainties an order of magnitude greater than what you see in some of the uranium lead data. And yet, in terms of accuracy, we got the right ages. We got the same ages as they were seeing down here. So we were able to pin these particular ammonite zones to these ammonite zones in Tethyan and say that's where the correlation takes place. Previously, with no ammonite species in common, there was no way to correlate between them. So this was a terrific start on doing this kind of work. But the uncertainties are too big for what we want to do. Here's an example of one of the isochrons we got during this study, trying to pin down what is the Lydidian stage in this particular unit. And we got a very nice isochron. This is a good uncertainty for what we were used to, less than about 0.5%. But we need to have it better than that to look at this 400,000 year eccentricity. So how can we get that down? That's one critical question.
And you could remind them the decay constant is 75% of that,
right,
plus or minus 1.47 million years.
Right, so that's one of the first things we can do. If we're comparing the age of, my mouse is stuck. Let's see, here we go. If we're comparing the age of this sample to this sample to this sample and saying, what is the duration? What's the amount of time elapsed between those sections, samples in a section of core? Then we can ignore the decay constant uncertainty, because all it would do would make all of these a little bit younger or a little bit older. So the duration would be unchanged. So we can take out the decay constant uncertainty, and that helps tremendously. But there's another thing we can do. We can note that this sample and these two, just as an example, we know the stratigraphic sequence. So we can look at each of these. We've got the younger age, it's in the right order, that's handy, and a very tight uncertainty on this one, that's helpful. And here we have a comparison. This is the uncertainty without the decay constant. This is the uncertainty with the decay constant included. So we've already cut the uncertainty in half in that case. And we can look at this third one up here, and we get an even tighter age. That's really nice. The uncertainty without the decay constant, 0.83. The uncertainty with the decay constant, with the decay constant and without the decay constant, it drops to about 0.4. So 3 very nice isochrons, but the uncertainties are still a little larger than we would like. We can use Bayesian statistics to refine these uncertainties because we know these are in the correct stratigraphic order. So I'm going to show a hypothetical case because we don't have enough data in any one place to do this. This is the relative sample sequence. So we've put our largest uncertainty at the bottom in the oldest sample. And as when we went up in the section, this one had a much tighter uncertainty, closer error bars, and the top one in our section, the smallest error bars. What if we went into this section and sampled very tightly in between these samples? So instead of sampling over a couple of meters, we started sampling every 200 centimeters, something like that, within the core. We could theoretically get a bunch of other ages. What we've done here is inserted randomized data. We created, using random number generator, another set of samples in between these that had the same range of uncertainties attached to it. So in doing that, we have some theoretical data that could match the kind of data we would get out of this same section if we actually did the analyses. We didn't have enough samples or enough time to do all of that. So if we sampled much more tightly, we can then take advantage of the sequence, the fact that these get sequentially younger as you go up the section, and that limits the possible range of the uncertainties. You know that these samples have to be in that order. The uncertainties can't be as large as way out here. Each sample, each successive point limits the uncertainties on the points above and below. And this is what Bayesian statistics does for us. It's mathematically a little bit messy to do it accurately, but we can do it. So this is the result. The blue shaded section in here shows the reduced uncertainties using the Bayesian model. And you can see that they're dramatically lower in some cases and significantly lower in all cases, except maybe this top one. Of course, when you get to the end of your sequence, you have no constraint below it. So that uncertainty is going to be one of the largest ones you see. You don't have as good a control on that. But by doing this, we get our uncertainties in this kind of data, and this is about the same age, actually a little older than the Jurassic section we want to analyze in this study with Stephen Hesselbaugh and Jacques. And we've got uncertainties that are well within the 400,000 year eccentricity. So we're going to be able to see variations in that. We're going to be able to see whether that duration of the eccentricity changes back in time. We'll have good enough precision to do it. So I hope that's fairly clear. And I'll let Holly wind things up for a couple more comments.
Yeah, got a couple slides left. I just was going to say that people ask, well, how old can you go, or can you date a slate, which is a metamorphosed shale? What happens if you try to do that? But this was one of the very first Precambrian age, and it's Archean actually, and it was really good result. Now keep in mind the decay constant uncertainty is in there. You see plus or minus 14. We've been looking at plus or minus 1.8 or whatever, but it's a percentage based, largely controlled by the uncertainty on the rhenium-187 decay constant. And that uncertainty is about 0.31%, the uncertainty added by how well we know the decay constant. So again, half to, it varies a little bit. A half to, I think I said up to 70% of that 14 is uncertainty that is put into the age through the decay constant. But this was, we were able to show this was the very first one dating a slate in the first Archean age, dating way back in time. And of course, there have been some, this was 2009, I think, yeah. And this is the group that was working on that. And we realize now, not only with sulfides, as I mentioned in the beginning, that we can go way back in time in very, very young things, but we can do it with shales, with an organic component.
I'd like to add one comment. In this paper that this isochron came from, we actually analyzed two correlative sections from two different drill holes a few miles apart in this section. And there was a volcanic bed in it that had covered the section. So we knew we were at the exact same place in the drill cores, and we got the same age well within uncertainty. for the
zircon.
two different, no, not of zircon,
for
of
the two,
two
yeah.
different shales from the same section. So we had a lot of confidence that we were getting an accurate age as well as a precise age.
Right. And this is just for those wondering, you know, how far can you take it? We can look at slates, and each case is another slate might not work. I mean, each case is geologically unique, and that's how you have to approach it. And then compromise of the clock. I mentioned this at the beginning. Oxidation is one, and maturation of hydrocarbon in a shale. A lot of the sections we looked at that were supported by industry were either just under maturation at or just over matured. So that was all, I mean, it was great that we got to work across that boundary and look at the effects of maturation on the chronometer in shales. And sometimes it all depends. If the maturation happened very close in time to the depositional age, we could still get the age within uncertainty of the shale. If the oil, you could see here, this is half of a drill core. It was wet, we wash it. This is tin foil. We have to wrap it because it'll fall apart. We cut it, and this was laid down on a paper towel. I mean, basic common sense. I wonder if there's free oil in this. And we had stuff that was just running oil, and you could lift it up after a few hours and you found out where there was hydrocarbon had formed, free oil in this section. And of course, you know, you could try to date in between or around this, but everything would be kind of suspect here. But what matters also is if this oil that was generated by maturation of kerogen, if it actually moved or if it's still in place. If it left the rock and some other fluid came in pushing and replacing it, I mean, it'll try to move and move toward a reservoir rock. It's more buoyant than the rock, different density. But there are many, many factors that are geologic based that go into thinking about working with shale. The other thing too is just a little picture here, bitumen flowing out of rock. This is in the Green River Formation in Western US. So
On a hot summer day.
On a hot summer day. I mean, but it's not because of the heat that it's melting. There were other places where bitumen was exposed. That is a melt because it was squeezed and moved forward, moved out in the outcrop and actually became exposed. So, and you can look in these three papers on your own, but in addition to dating the shales, the source rock, most of it successfully because of the strategic sampling, we also are dating the timing of migration. You can date arrival of oil in a reservoir rock if it equilibrates with that reservoir rock. There are many things. It's not, you know, people used to say, what are you dating? The formation of the kerogen, the migration? The answer is you have to be thoughtful with every system in some both, or some aspect. You've got both ends of the stick. So that, I mean, there's a lot of detail. These papers will provide those of you interested in seeing beyond the clock in nice, pristine, undisturbed shales. You can look a little further. That's it. That's all we have to say. I fear to look at the clock, but these are the primary sponsors, formerly Statoil, now Equinor, but these are the sponsors who put many millions of dollars into our lab and who really believed that we could figure out some of this stuff, which was so important for their work and understanding and their exploration models and so on. And we feel very fortunate to have that support, and I want to acknowledge them. And again, thanks to the AstroGeo team for their interest in finding out how radium osmometer isotope and I have to say, both of us geologists apply the chronometer, and we meet the challenges of working with a heterogeneous planet Earth. You know, we're starting with a mess, and how do we tease our way out of that mess to capture real and meaningful time that we can then apply, is we've shown in the examples in the talk. Well, thanks again for both of us.
Okay, thanks a lot, Oli and Judy. And so we are now open for the question. I saw that Urs unfortunately just left because he needed to go to another meeting.
Oh, okay.
But,
oh, he came. Urs came.
Yes, he was there. He was there for all the talk. But he just left. He just left. No, but I'm sure he would have some question. But other people may have some question. I'm looking to just raise a small hand if you have some, or comments, or
Hi there. Thanks for this very nice talk. It was really a pleasure. I'm really quite intrigued for the work that you're proposing for the lower Jurassic. So we did quite a lot of work on the MOCRIS and now on the pre-score, in determining indeed the stratigraphic framework for those records. And you know, I should probably aware that there's quite good age constraints for the Triassic-Jurassic boundary and also for the Tuacian, but everything in between is kind of, well, open in terms of absolute or numerical ages or whatever one wants to call it. So I guess there the rhenium osmium dating really comes in as being really useful in checking and providing much better age constraints for those time intervals. Now in your, what Judith was showing, in your Bayesian modeling, you infer, so let's say that you have 3 good isochrons, rhenium osmium isochrons, and you would need potentially many more. But how many would you really need? And what is your plan for the lower Jurassic? Because ultimately, I mean, I guess one would only need to get some tie points, right? So let's say indeed for the Sedimentary boundary, or for the attention Sedimentary boundary, or for any other time interval, if one were to get like 3 or 4 isochrons closely spaced, that would be enough to get a reasonably good isochron. Is that right? Or kind of an H, maybe I should say.
Yeah, but I think our planned approach to this would be to take some nice looking sections of the core that we think we can trust over this whole section that we want to look at and see where we're getting good consistent data. Every once in a while, there's going to be disturbances in the sedimentary section, whether it's a hiatus or input of some plastic debris from a different source or whatever it may be. And so there may be places where we don't get perfect isochrons. We'll go to those places where it's the best. And then when we have, say, 2 or 3 good isochrons in a row, go in and try to put a couple more in between those so that we get a tighter constraint. We can't afford to go into the section and, you know, go every 2 meters and make an isochron. Be here for the next decade.
Of course.
But if we can do the best sections that we find in a reconnaissance survey of a handful of isochrons, and then go in and try to get refined data in multiple sections, then we can use those to look at the duration of the eccentricity through those more limited sections. But if we have several of those, then we have some faith in the result.
Yeah. And are you in principle planning to work on the entire lower Jurassic or on targeted intervals?
Would like to do the entire lower Jurassic. It's a matter of time.
Yeah.
And cost and limited funding. But we will be able to go very far with this. And I emphasize too that we're going to be working as a team together on, you know, sections that may be of more interest. And I also want to be sure that people realize that it's not going to be perfect in everything that we look, but we're going to find those really good intervals and then take them, as Judy said, closely space them apart. Right now, analyze in between and create what the figure shows here. Right now, my PhD student in the other room there, he's looking at some stuff from the upper Jurassic from drill cores on Svalbard. He has some really tight ages that the line is so good that the regression kind of undercuts the decay constant. He has other ones that are 130 plus or minus 6, 8, 10. And it doesn't matter how many points he keeps putting on there, it's not going to get much better. Sure, as n goes up, things get a little better. And, you know, if the amount of scatter is similar, you know, if you have even more, then it goes worse. But there's no way, we know when there's no way we can improve on something, and we know where to stop. And we know when we have something good, and that will be determined working as a team and with a reconnaissance thing. So I don't want to give the impression that everywhere we go, we'll have a golden spike, but we will. I can say as surely as there will be sections that won't work, I can say 100% confidence there will be sections that will work very, very well for everybody's interests.
Yeah. Excellent. Great. Thanks.
Any other question? I don't see some immediately. I have one. maybe it's totally elementary, but I was a little bit confused at the beginning. The way in the slide where you start from 14 points and then suppress some to get only 8 and improve the statistics.
Mhm.
Can you go back to this slide?
Yeah, sure. It's one approach.
Yeah,
that
it was
ties-
in the beginning.
Yeah, it ties to geology, the way we treat, that was very early on. That talk was given, yeah, here it is.
Yeah, something like that. Yeah. So my question, so suddenly I don't understand exactly how you derive the uncertainty, because what, for example, if you keep only 2 points? If you keep 2 points, only two data points, you will have.
No, we kept almost all of them. We took off 2.
No, but if
Oh.
you keep only 2,
Oh,
after you keep only 2,
quite good.
then the line, you will have a line that will pass exactly through your 2 points.
Right. But you can never publish 2 or even 3
No,
point.
but my question is, what would be your computation of uncertainty in this case?
You can't do it. You can't
Yeah.
assign an uncertainty to 2 data points. In our opinion, 5, 6 data points is probably the minimum.
So yeah,
uncertainty.
just repeat exactly how is computed your uncertainty.
Yeah, it's based on the uncertainty in the measurement of ratios on the mass spectrometer. That's a pretty minor component on it. It's based on the uncertainty in the spikes used. In order to determine a concentration, we have to put a known amount of rhenium in a solution with the unknown, the sample. And that spike solution has an uncertainty associated with it.
Yes.
And then the uncertainty of weighing the sample, a weighing error in the balance, that's pretty minor. We have something called a double spike where it goes away, but that would not involve these shales because we have single rhenium spike and single osmium spike. And then we have the uncertainty associated with the blank. We have to know our blanks very, very well.
Okay, but do you evaluate them and derive for the data point one uncertainty?
Yes.
Point. So
Right.
you evaluate an uncertainty for each data point.
Yes.
Okay.
And there are papers that blanket say, oh, I'll be generous. I'm going to apply an uncertainty of 0.x% to all my data point. It couldn't be more uncertainty than that. This just drives me nuts because an uncertainty is calculated for every data point. And sadly, in the literature, you can find people, I don't know what they're thinking, but they assign a blanket uncertainty to all the points. And that's incorrect.
But so it would be nice. So, but here on the plot, you don't report the uncertainty.
Not for each point, but you can see the ellipses in the little inside the box, which I made. You can see they're different sizes.
Those are a little bit bigger.
Okay.
They're ellipses too.
Smaller because it's proportional to
okay, so you want to say that these ellipses, which reflect the uncertainty, are so small so that they are not really seen. But if they were enlarged, you would see so the uncertainty is the small ellipse. Is that what you want to say?
You would.
The a priori uncertainty of the data.
Yeah, each of those points in those purple boxes is a different size and shape.
Okay.
They're similar shape usually. But here you can see this one has more uncertainty, probably in the rhenium because it's flat. It's flat here, so there must have been.
Obviously, these uncertainty are optimistic because the line doesn't go through the ellipse of uncertainty.
No, and that was, I here you can see two different shapes for the uncertainty. And if you blew this up, you would see these are ellipses. They're ellipses because there's an error correlation because 187 osmium is in both the X and Y.
And the line for the determinant, which try to fit to all the data, is away from the ellipse. So it means that, that the ellipse was an optimistic view of the uncertainty, no?
Well, that's why you calculate the uncertainties. Some people, when they assign uncertainties, they blow up this ellipse. So all the ellipses, you see, because the ellipses don't touch the line, this is terrible. 1/26 for MSWD. It's way too high. That tells you that these points have real geologic variation from
Okay.
point to point. Yeah, I mean, that's what it tells. But you know what, again, some people do is they blow up the uncertainty on these ellipses unjustly, and then all the ellipses touch the line suddenly. You know, that's why you calculate uncertainty for every point. There's a real uncertainty assignment.
Okay.
And when all the ellipses touch the line, you will still have the same uncertainty. You know, I think, yeah, in the age, but this will come down to, you know, 5 if everything touches the line. This is a measurement of the deviation. Square of the deviate mean square. Wait, yeah, of these small dots away from what is your
it probably means square weighted deviation or something like that.
Yes, that's right.
Okay.
So ideally, we'd like to have this close to 1.
Yeah, shales, it's hard to get sometimes, but we had some that were less than 1, which probably means we're.
But of course, yeah, the estimation certainty is probably 1 sigma, and
It's 2
sigma. Okay.
Yeah.
But
Yes.
you may take 3, which is without any problem. That's okay.
And if that.
Yeah, it's a little bit more clear now, but because I thought that no uncertainty was computed on each data, but it's not the case. So that I understand now.
Yeah, there is an instrumental analytical uncertainty associated with each measurement, but then there's a host of other factors that are propagating into the uncertainty that we report.
And as I said, this is 16 years ago, this data, but it was a set of slides I made that I hoped nicely illustrated, but now we've cleared up your question, which is a good one. But just to say though, I don't think if we had this kind of a data set, you know, and we had the funding to work with this these blank event cycles, we probably wouldn't pursue that. It's just a little too unstable. And you saw some of the Permo-Triassic or latest Permian ages we had that had less than 1 million years, really lined up points. So that was just to illustrate, you know, how we look at which samples deviate with the geology. And again, you know, now we have, and also trace metals, you know, all kinds of things that we will take that data from a shale section, a whole suite of trace metal data and rock eval data, a lot of things that will help us to work with how good the isochron is, how much confidence we have, should we pursue further, and yeah.
I just put this slide back up because it shows the kinds of things we put in the data table for every step.
Okay, yes, you have the sigma,
2 sigma
uncertainty estimated for each data point. Okay.
Yeah.
And this is the error correlation between the X and Y axes on our isochron plot. And a data table in a published publication would also include a host of footnotes down here to say what was the blank on these measurements, or multiple blanks if we measured it several times during the study. What was the uncertainty on the spike calibrations for these particular runs, what spike was used, and so on. Just a host of information so we can trace everything we did during the analyses.
Yeah. And Jacques, you used the word, oh yes, I'm just going to be sure this is clear with everyone that these are the estimated uncertainties. They are the calculated uncertainties. They're real calculations based on input from blank, the osmium isotopic composition of the blank. If it's far away from your sample, then it's going to enlarge that uncertainty. If it's very similar to your sample, it will reduce. It will be a less of a factor in the uncertainty. And as I said, blanks, uncertainty, and the spike calibrations, all of those go into that calculated 2 sigma error.
Okay. Okay, thank you. And Matthias has some question?
Yeah. Hi, Moses.
Hi.
Hi.
Thanks a lot for the clear presentation. I think my questions were about uncertainty, and they're largely answered by the answer to Jacques' question. But so you clearly expressed that the decay constant is quite important. The analytical error is relatively small, so there is then the tracer or the spikes. So I was just curious, for the uranium lead, they made the Earth time spike for interlab comparison, and so how is that for rhenium osmium interlab and the tracer? And yeah, I was curious about that.
That's a great question. In the beginning, when we started working, we started with molybdenite. I showed you the evolution of rhenium osmium applications in crustal rocks, but we realized early on we had a sample from a milled sample from a deposit in China that one of our colleagues, she's now retired and she's a chemist, Du Dao, and she said, "Oh, if I had it to do over, I'd be a geologist." I said, "Well, no, it's cleaner over where you are, the chemistry." But she had this milled sample, and she asked if we would measure it because they were measuring and they're trying to use it as a standard. Well, and that is published in a couple papers. But shortly thereafter, I realized we've got to have a NIST standard, some kind of interlaboratory comparison. We had an in-house one for a while that we were sharing, but it wasn't official. I should say, so we need some kind of reference material that's marked by NIST. And so I, together with John Morgan, we had an NSF grant to put that standard together. And so at the time, I went to the Henderson molybdenum deposit. Colorado Mineral Belt here is famous. My whole thesis was, I started out as ore geologist, I still am, ore deposit person. So I went to the mill and asked if I could have a bag of, they have froth flotation. That's how they separate and get the molybdenite out of floats. It's like chocolate milk silver bubbles on a soapy mixture. And so they gave me a big bag of a very finely milled powder, and the age of that is we know it very, very well. And that's the age of whatever they were mining in whatever drift at whatever level underground that day. It doesn't matter what the age is. But even within that finely milled powder, and I chose Henderson, let me back up, because it's young. The rhenium is not too high. Generally, those kind of molybdenum deposits, there's a lot of rhenium to go around.
There's a lot of moly.
There's a lot of molybdenite. So any single molybdenite, that was my theory at the time anyway, it's not too high in rhenium. And it's young, about 28 million years. So the amount of radiogenic osmium isn't too big, but it's easily measurable. And I think it has about 11 ppb, or ppm, sorry, rhenium in this, yeah. And some at ppb level radiogenic osmium, of course. And so I thought, well, this will be a standard good not only for labs that are doing sulfides and dating ore deposits, which was my initial wanted to bring that online, but it will also be good perhaps to be used in labs that are working with the other meteorites, shales, eventually other media trying to do rhenium osmium, because there's not too much radiogenic osmium to be thrown around. Nobody wants to have molybdenite would be a huge contaminate for people working with meteorites where they have very low radiogenic, very low high osmium, but very low ratio. So anyway, that was our thought. Yeah, and so that there you can purchase that. It's a $300 a bottle. It's a standard, not a standard. It's a REM reference material. I think it's 8599 or something like that. It's a Henderson molybdenite.
When we did that study, at that time, there were, I think, 3 rhenium osmium labs in the world that would touch molybdenite.
Or 2. China,
China.
And Rob Creaser.
But fundamentally, we did the work with Rob Creaser. We invited him to join us on that study and we split bottles and shared them between the labs. And so we had an interlab comparison. It would have been nice to do some, international round robin, but there were no labs doing it.
We were the only ones doing it. And Rob was like our round robin of 2. So we had some funding to give him so he could run that stuff. It's published.
But now many people have analyzed it all over the world. And yeah, and it's serving reasonably well as a reference material. The interesting thing, though, is despite all the effort to get a homogeneous sample, the rhenium-osmium ratio in that sample, or the actual concentrations, the actual concentrations of rhenium and osmium vary quite a lot. So it cannot be used as a standard for measuring, say, rhenium-187 concentration. But the age is the same, always.
Yeah,
it comes out the same.
It's a reference material for age.
Proportional up and down in the total content of rhenium in a given molybdenite subsample.
Yeah, it's an age reference.
There's also a question in the chat. I don't know if if you want to read that.
Question in the chat.
Oh yeah, hold on.
It says,
I don't have my webcam.
What is your opinion on the different ways to calculate regress data? For example, isoplotter, Monte Carlo method. They all produce slightly different ages.
You could take that.
Yeah, well, the Monte Carlo approach has appeared in the literature just in the last couple of years, applied to rhenium and osmium. And I'm not at this point convinced it's going to replace the isoplot. It may be a matter of familiarity as much as anything, but I don't see that we're getting new and better information from it. I'll admit it's not something I've dug into in great detail. We've looked at the results. I haven't picked apart the program that is being used to do it. So it's a little premature for me to judge. But you get these clouds of data, and it's just a little less clear to me how to interpret those. As I say, it may be lack of familiarity on our part. It'd be nice to have something that will supersede Ken Ludwig's isoplot, because eventually we're not going to be able to run it.
Yeah, there is a program. But
there's this new program coming out, and the Monte Carlo approach is another.
But that's a study to be done. I mean, an examination to be done, comparing things rather than, okay, here's a new thing. And
it's going to have to be a combination of looking at the actual program itself and exactly what goes into the two different programs mathematically, and whether you can say that this approach is more valid than another approach. We haven't gone that far.
We haven't used it. So, I mean, I guess I would like to be able to give a more thorough answer, but we don't see that there are any issues with the approach that we're using. What is it John Morgan always said to me? If it ain't broke, don't try to fix it. That's in the lab. The great John Morgan, the meteorite guy. Yeah.
So that's a bad non-answer to your question.
Yeah. Was there another question?
Okay. So is there any?
Oh, Danny. Hi, Danny.
Any other question from the audience? Let the time. Don't see anyone.
Yeah.
So if there is no other question, maybe you can stop sharing your screen so that we recover you in plain view. Did you? Yeah.
Oh, much better.
Things.
Yeah, it's better like that. And thanks again for your talk, which was very clear. And so it gives a better view of what this rhenium-osmium measurement can do. And thanks to everybody for attending. And I will soon put this on the YouTube station, so Steve at least can see what he missed. Okay.
Thank you all.
To everybody.
Thank you.
Good to meet you electronically.
Yes, and thanks for coming.
But unfortunately, there is a bad thing about electronic meeting is we just now, in half an hour, we have a party with nice champagne, and you would have been invited all, but
that means there'll be a second party when we get down there. Yeah. We'll be back in Oslo. We leave. We'll be there most of the rest of the year. I mean, in and out a bit here because my lab is here. People think there's a lab in Oslo, but it's here. So, but we'll be in and out, but largely at UIO, and we're leaving Monday. We already were there in January and a few weeks in March, so that's normal. We're moving back and forth.
This time we're timing it to get to the AGU meeting.
Oh, yeah. Okay, you are coupling with the AGU. So you will meet some of us in the AGU.
Great.
Oh, you're going to be there. Good.
Yes, some of us will be there.
But please, if you see us, just give us a kick if we walk by you, because I'm not going to remember everybody's photo on against a bookcase.
Okay.
Okay.
So goodbye to everybody, and
Thank you, Jack.
I will see you eventually the next time. Bye.
Bye-bye. Bye. See ya.